So just I remind that I was proving the following theorem in at the end of last lecture about persistence of generating function. And let me maybe formulate before I kind of go to what I was doing yesterday. Let me formulate several kind of versions of the theorem, and I will prove this. Okay, so version number 1. So you started with cotangent bundle of some manifold, and let's say assume that this manifold is closed manifold, and if not, then it could be non-compact, but then what I will be doing will be with compact support. So you have this cotangent bundle, and then in this manifold we studying Lagrangian submanifolds of this manifold. So what are kind of in general what are Lagrangian submanifolds in cotangent bundle? So of course there is this zero section. So I was kind of writing yesterday. Okay, yeah, I was writing yesterday letter n, but let me switch to m. Okay. So like 0m, this is a zero section there in this manifold, and you can take any function on the manifold, and this function give me so let's call it LF. It's a graph of differential of this function, or like you can like slightly imprecisely write it's a p equal df dv q. So if you like call q coordinates, so this is in some sense perfectly fine, because there is a always in cotangent bundle, of course on the manifold there is no canonical coordinate, but whatever local coordinates I can choose, there are dual coordinates in cotangent bundle, and so therefore everything kind of looks exactly the same in whatever coordinates you have. So this kind of notation makes sense. So you have this LF, and the question, what else? Of course, and then like every for every Lagrangian which we have, we can take this form. So symplectic form is this equal d of this canonical form PDQ, and we can take PDQ restricted to this L, and this form, because it's a Lagrangian, this form is closed, and for all this example which I gave, this form is exact. And I will concentrate on exact Lagrangian manifolds. So kind of like I'm not interested in anything else. So all my Lagrangian submanifolds will be exact. And so then manifold is called exact if this form is exact. So for instance, this has this. So question, what are exact Lagrangian submanifolds in cotangent bundles? You can have this example, or you can take a Hamiltonian isotopy. So that means you take some family of function on cotangent bundle, and this family of function generate a kind of Hamiltonian vector field, and you can just consider this family of vector field generate some Hamiltonian isotopy family of symplectic transformation of M, and you can do this, and then we can take a LT equal phi t of M, phi t of L. So given already, or phi t of M, say phi t of 0 M. So this is a kind of, so all these are of course like this. You can of course any of this Hamiltonian isotopy. So question, are there any other Lagrangian submanifold, exact Lagrangian submanifold of cotangent bundle? So this is a so-called nearby Lagrangian conjecture. So nobody ever seen any other manifold, and this is like one of famous open problem. So are there any exact Lagrangian submanifold of cotangent bundle besides this? So I personally extremely doubt that this could be true, but who knows before this.
What does Gromov think?
No, it doesn't matter. No, I mean it doesn't matter what Gromov think about this. Well, I don't think Gromov would dare to say. I think Arnold probably thought that it's true, and well, kind of. But things change. Things change. Also, I think this is a kind of not completely good question, because you should ask what Gromov thought, and then you say at what moment of time, because the answer is time dependent. Okay. Okay. So anyways, but we are not going to we are not going to solve it. Maybe if you have time or whatever, we can fantasize how this in principle one can try to prove that, but we are not going to do anything else. But let's take this LT, which of this form, and then the theorem that this Lagrangian is still almost like this, with slightly different, and it is not this graphical, but what kind of we call subgraphical. So that means that the theorem that given such isotopy, and let's fix kind of some finite time of this isotopy. It's important that not forever this isotopy going. And then the statement is there exists some big number n, and there exists some family of functions on our manifold M cross Rn, such that such that f0 is just some quadratic. It's a non-degenerate quadratic form. Non-degenerate. So I will write q of so let's call, say, coordinate x coordinate here and y here. It's a q of y. It's a non-degenerate quadratic form. Non-degenerate quadratic form on Rn. So you have this, and ft is equal this q, and I will write plus some epsilon t of xy, where this is a function with compact support. Which compact support such that ft generate our, so maybe I actually write not write q, right? I was continue qy such that our ft generate our lt in the following sense, that lt is given by equation p is equal, so dft of qy over q, and dft of qy over dy is equal to 0. So I will explain geometry of this last time. So that means that we're taking cotangent bundle of M cross N. There you take a graphical manifold taking this one, and then in the cotangent bundle of M cross Rn, this say call coordinates qy, and there is a dual coordinate to this, which we'll call p, and I don't know, some u maybe, and so such that like canonical form is p dq plus u dy, and and then we take this our Lagrangian, we take Lagrangian L ft, which sit in this cotangent bundle, intersected with this subspace which given by equation u equals 0. So that means we consist of form annihilating fiber of this fibration Rn. And then there is a what is called symplectic reduction, as I say, the projection of this cotangent bundle of M, and the image is give us our, so the image under this projection, kind of like under this projection is our LT, right? So that's what we have. So this is a theorem. So in fact, of course, this theorem can be, and I will be like exploiting this, formulated slightly more kind of geometrically. So to say, well, you have a space of the generating function, quadratic infinity, and there is a projection to the space of Lagrangian where this construction, and this projection is in fact self-fibration. So that means that this kind of property, like extension of continuation of homotopy, work parametrically, except of this strange feature. Like in order, it's not kind of like on the spot as I wrote. This is of course not self-fibration because this n depends on t. So if I have to kind of continue a little bit more, I need to increase n. So what kind of, in order to make it kind of precisely, you need to replace Rn by some kind of R infinity and have this function quadratic at infinity, but with not kind of prescribed. So, okay, so anyway, so this. But kind of modular this strange feature that this kind of this number of square have to grow, that this is a self-fibration. Okay. So, and then I was explaining how we do that. That like what is the kind of mechanism? Mechanism is kind of exactly the same how I was proving Arnold conjecture for torus. That I took this Hamiltonian isotopy, well, phi, this Hamiltonian isotopy, and split it into so this is a 0 and this is phi t, and you have a this phi 1 over n, etc. And you present it as a composition of many small symplectomorphisms. And then you take a product. You take a product of graphs. So what we were doing, we were taking the following thing. You took R to n, and then we take a product of n copies of R to n, and here we took 0 section. Here we take a graph of, like, let's say, first. So we presented that phi t as this composition of, as a product of psi n, say psi 0, where psi j is phi j minus 1, right? So phi j minus 1. So you just kind of like present it as a product of small diffeomorphism, and then here it's a graph of diffeomorphism psi t, psi 1. This is a graph of psi 2, etc. And important here, we take a symplectic form here, omega, minus omega, omega, and minus omega. Okay, why I wrote R to n? Because I was proving first for the case m, this our m is equal Rn, and then this is R to n. So what we were doing is this R to n. And the reason why it was extremely important that it's R2n and not anything else, that this is a Euclidean space, symplectic linear space, and in this symplectic linear space, there's an enormous number of Lagrangian subspaces. We really freely can change different Lagrangian, which what we did. And then we said that there exists some kind of elementary set theory, here kind of set theoretic argument, which says the following thing. So if I take this Lagrangian times this graph times this graph times this graph, so what I call L times delta odd. So I take a okay, so this each of this graph is very close to diagonal. So if I would replace psi1 by identity, it would be diagonal here. So this you can take a like delta odd, or you can take a L times gamma, where gamma is a product of all graph. And this gamma is very close to delta. So this is a kind of, in fact, very interesting thing. So so we have something extremely non-small map, and presented a composition of small. And then suddenly product of graph of small is close to product of diagonal. It was not true for original one. But now they are close, but they are close in this kind of infinity norm, right? Not in kind of like Euclidean norm. If I would write Euclidean norm, they would be extremely far. But in this maximum norm, they are close, and that's what we use. And then we chosen some appropriate Lagrangian, which is transverse to all of them, and then this linear spaces you can write as some quadratic form, and this graph, our addition of this gamma was giving some this epsilon addition there, and that's how we were getting this quadratic form and plus epsilon t. So there is I didn't write it down explicitly, but in fact there is some formula which due to Chekhanov, who like explicitly wrote like if you add one more R2n, precisely how the generating function change. There is some kind of addition formula. So you can work it out, and this is it's pretty straightforward, but because of this I told necessity to change variable, there is something to do. Okay, so that's what we were doing yesterday. So now let's continue. So this argument proves this theorem which I formulated for the case of Rn. So like our first task is extended to other manifolds. And this is in fact amazingly that, okay, so there was as I told, there was originally, it was proven by Laudenbach and Sakharov, and they work hard to cover general manifold by chart, and out of this cook up something global, which was a kind of big mess. And then Chekhanov had this great idea that instead you can use the fact that any manifold embed in Rn. and then kind of like how it works. So you take so now we have any manifold M. There's n-dimensional manifold, and we embed it to some Rm of some big dimension. So now here you have a cotangent bundle of M, and you have a cotangent bundle of Rm. So how they kind of like related with each other? So that, for instance, why it kind of became so dirty? Okay. So this is our Rm. This is our M. And you can take cotangent bundle of Rm and restricted to M. Just consider kind of all fiber over point of M. And call this sigma. It's just total space of restriction of cotangent bundle to M. So this is a coisotropic manifold. This is a coisotropic manifold, and it's kind of what are direction of degeneration? The direction of degeneration is precisely form which kind of like annihilated on complementary dimension, and when we quotient by them, then we get precisely cotangent bundle of M. So therefore, if we have any Lagrangian submanifold in the big manifold, then we can, and suppose it's transverse to this isotropic thing, we can intersect it and project it down. And if this was given by generating function on manifold M cross some big Rn, on this Rm cross Rn, then the new one will be given by restriction of this function there. So this sounds obvious, but implementation of this is not so trivial. Kind of it requires some care, because what's going on? Remember, we started with zero section. What we're doing? We started with zero section in cotangent bundle of M. So we started with zero section in cotangent bundle of M. Of course, if you take this zero section in Rm and do this kind of reduction, like intersect with the sigma and take a projection, then you get exactly this. But now we started to have this manifold have some kind of Hamiltonian isotopy. And the question, we need to extend this Hamiltonian isotopy to the whole cotangent bundle. And of course, kind of say, oh, it's trivial. Take this Hamiltonian isotopy, just cut it off there and do. But then what can happen? That you start to kind of move this one, and then some other pieces of this Lagrangian start to move and intersect. And we get that this, as we're moving, it will be, by reduction, we will getting not just our manifold, but something else. And so therefore, you need to care that, like when you do all this cutoff construction, nothing kind of pulled back. And this is a subtle, because this is like main difficulty in Hamiltonian mechanics. Because if you have a Hamiltonian function and you're trying to cut off, that in this cutoff region you create enormous kind of motion along this one, right? So you have a Hamiltonian and you cut it off, and then in this region where you cut it off, this gradient is very big, and like things start to move like crazy in this direction. So therefore, the fact that you do this is require care. So this can be done, but require care. So that's why kind of like we wrote with Gromov this paper, which I actually talking now, that's called finite dimensional approach. And the biggest like part of this paper is some chapter 2, and this chapter is just precisely about cutting off. So just kind of like it's a extremely kind of boring thing which kind of nobody can read, but that's what we're doing. We're just proving that by cutting off you can do cutting off in controlled way. Yeah, so it's kind of straightforward, but it needs to be checked. Okay, so that's what I just wanted to say. So I'm not going to do that. In this case, it's not difficult. In this case, so but I just warned that this is the case. Okay, so what?
why you are not believing co-initial. Co-cause article of single approximation.
This is also related to this as well. Okay. Yeah, so this is the kind of like, it is a true fact that like, I think like most mistakes which were done and kind of especially initially in the paper on the symplectic stuff was in kind of not doing correctly cut off. Okay, so therefore what we did, so that means that we pass from like this RM case, we pass to M case, and this.
Can you just expand about what exactly one has to be careful about? I mean, this flux around the manifold that you were talking about.
So you have a Hamiltonian on cotangent bundle of M, and we need to extend this Hamiltonian. Of course, for instance, you can make it independent on p coordinate, on this extra coordinate, and just say pull back this Hamiltonian just to the thing. But then our manifold is embedded in this Euclidean space, and there is of course, we need to very kind of, we don't have much space to cut, right? Because it can be like curved, and so therefore, when we cutting off our Hamiltonian, we really kind of multiplying by some cutoff function with large derivative. And then what we need to check that this Lagrangian, which we initially extended, that Hamiltonian flow may kind of start to move it and push it back to this part with which I intersect. And therefore, I can create some. So this is doesn't happen here, but kind of you have to care about this. Okay, so now next thing, we want to prove Legendrian version of this. So now you kind of.
I'm sure it is much more subtle than just the usual trick of rescaling thing and making things look close far.
No, you cannot rescale here because you don't have much space. Yeah, in Q direction you cannot rescale. In Q direction you cannot rescale. But luckily here is kind of like everything fine because this Hamiltonian for P dot is equal dH over dQ, right? So therefore, like derivative, big derivative in Q direction create motion in P direction. So it's kind of not really. Okay, so now the next thing is Legendrian version. And first, there will be two Legendrian versions. One, we take a one jet space of M. So which is, as we discussed, is just cotangent bundle of M times R. And now again, I take a zero section here. So now you this form, say PDQ like minus dz. There is a contact form here, and there is a zero section, which is now p equals 0, z equals 0. This is a, let's call it, maybe I also continue call it 0m, this one. So this is Legendrian submanifold, and now we're saying, okay, suppose you have a contact isotopy. So now, like phi is a contact isotopy of our one jet space, not Lagrangian. So if you have a Hamiltonian isotopy of the base, it generates contact, it leads to contact isotopy one jet space, just by adding to Z this corresponding Hamiltonian. But of course, this is a much kind of larger class of deformation. So in particular, it need not to be when you project, you start Lagrangian and project back to cotangent bundle, it may still be self-intersecting, it's not necessarily embedded, right? So it's not, does not cover cover isotopy in the base. And so you have this contact isotopy, and still turns out the generating function persists. So again, there exists like statement exactly like here, that you have a family of function such that like before our, let's call it, say, lambda t, this is a phi t of this zero section. This is a moving Legendrian, and this moving Legendrian is again given by the family of the same function, but now it's given by equation p is equal df of qy over dq, df of qy over dy is equal 0 as before, and one more, that z is equal function itself, so ft. Okay. So you have this. So that means that so if I would not have a variable y, it will be just graph of one jet of function. But now this is like the same way reduction of the other one, but in this contact case. So this is the theorem. So as I thought, first theorem is like first people who published it. It was Laudenbach and Sekharov, and like the idea came from paper by Chaperon, who in turn kind of reworked the proof of Conley-Sander. And this is a theorem which was proven several years later by Chekhanov. And the point is this theorem, of course, is proven several years later, but it could have been proven in 15 minutes because it's kind of immediate corollary of the previous theorem. So I will deduce this thing from symplectic version. So what's the proof? So let's look at this one jet space of M. As I said, this is it's a contact manifold with a contact form PDQ is right minus dz, whereas this extra z is this coordinate. And then, as I was kind of popularizing this idea yesterday, you should think when you have a contact manifold, you immediately say that, okay, don't want to really do anything in odd-dimensional manifolds, so I immediately want to go and live in even-dimensional space. You symplectize it. So take a symplectization of this, and symplectization, as I told, can be thought of as you take a one jet space of M times, and I will write times r plus, and let's say call coordinates here, and then you have a symplectic form on this one, which is a PDQ minus dz times s, and you take a d of this, right? And what is this? This is, of course, d of sp dq, and minus s dz, but I want to write plus z ds, right, instead. So I want to rewrite this one. So this is and now I just replace, I call this change variable, I call this u. So now what we see that this is just cotangent, this is a standard symplectic form on the cotangent bundle of T star of manifold M times like times R plus times semi-axis, where this z coordinate kind of, where s is a coordinate on the semi-axis, right? Yes?
So
But if phi t is a contact isotopy of the one-jet bundle, it need not extend to a Hamiltonian isotopy of the symplectization, right?
I didn't extend it. I will prove it. Okay. So have this phi t. Okay. So there is a okay. So there exists this phi t. Yeah. So in fact every what?
But there is also this, like, even if M is compact, when things are moving on M, now it's going to move on everywhere on the cylinder. Because you're replacing M by M cross some.
Yeah, you're too fast. Just wait. Okay. So I didn't prove it yet anything, right? I just wrote this one. Okay. So, but of course you have a given. So you have this this Legendrian, and of course every Legendrian is in symplectization can be symplectized to the cylindrical Lagrangian, right? So we have this. So let's kind of draw this model. So this is my S. This is my M, and this is this is S equal to 0, and this is this S equal to 1. And our manifold M, like our contact manifold, sit in this identification over S equal to 1, right? So over S equal to 1, we have this, and here you have our Legendrian sitting, say moving Legendrian, call it lambda t. And this, of course, Legendrian give us this Lagrangian cylinder. So, yes. So we have this Lagrangian cylinder, and initial Legendrian, of course, was nicely smooth up to this S equal to 0, because it was already 0 section. So there it was like this just plain product, so it was a smooth Legendrian up to there. But now this Legendrian is deformed here, but at this end it's kind of, it goes to 0, but kind of like not smoothly. But of course we can cut it off. We just cut it off, this Lagrangian isotopy in this part, and so we have a Hamiltonian isotopy, have a Lagrangian Hamiltonian isotopy such that here it's cylindrical in this part, say above S greater 1/2, it's cylindrical, and in this part I just cut off to 0. And now what about, so, and suppose we found this kind of like generating function. So first of all, what was a generating function? So if our Legendrian, suppose we have a Legendrian given by some generating function, then question, what a generating function give me this Lagrangian cone? So if my Legendrian was given by some generating function f of this kind of qz, no, f, no, not f of q, just f of q, they're just given by f of q, Legendrian, maybe of even whatever other variable, f of qy, then if I multiply it by s, this would be generating function for this Lagrangian. Because note that we have a z was equal z was equal to f, but f is equal dsf over ds, right? So therefore it's exactly as it's supposed to be there. So here also I have this sp. So before this p was df of dq, but now sp, it will be precisely correspond to this one. So I'm saying if you have a contact manifold, and you have in contact manifold you have some family of Legendre given by generating function in Legendre in context sense. And this was a function ft of q and maybe some extra variable. So now you have a multiplied by extra x. And in this new manifold, you just, okay, I'm just only talking about this part. So here you cut it off, I have no idea. But in this part where it's cylindrical, in this part I'm saying if you just take generating, so now on our base manifold we have a one extra coordinate, s. And so therefore instead of function f of q, you take a function s times f of q. And this times function s of f of q precisely in this coordinate will be generating for this Lagrangian cone, right?
But I'm still confused about why this family of cylindrical Lagrangians is Hamiltonian, because the original isotopy can just scale the contact form.
Why is this Hamiltonian? Because any contact isotopy always leads to Hamiltonian isotopy. So this kind of yes. So
the contact form is scaled.
the contact form is scaled by this Hamiltonian. You also scale this. Yeah, it have nothing to. So, yeah, no, you know what maybe what you kind of like trying to say is the following thing: that suppose you have a like in symplectization. Suppose you have some contact isotopy, and this contact isotopy does not scale contact form. So that means that corresponding Hamiltonian isotopy will be preserving this level. But of course, when you have a Hamiltonian isotopy, contact isotopy does not scale, that this level kind of start to change precisely by the scaling function, right? But it kind of doesn't matter. Okay. Okay. So yeah. So again, so therefore, what's the proof? So you take this. So you solve this for this function, then scale it back, and then reduce back. And here even there is no problem with cutting off. So the only again what need to be checked that when we're cutting off here, then there is no pieces which kind of go and intersect this one. But here it's very easy because okay, so this. But anyway, we have to be checked. Okay, so now final version, contact version, which I want to say. So this is a proof of this Chekhanov theorem. So there is a kind of another version of this, which kind of again more or less immediate corollary, which is called generating hypersurfaces version. So now you have again we start with some manifold. Okay, still going with M, and now I'm going to contact manifold with which I want to work will be projectivized cotangent bundle of M. And there could be, so it is called space of contact element. The point of this thing is a tangent hyperplane point on the manifold plus tangent hyperplane in this point. So as I told yesterday, so this is kind of like the name space of contact element. It's a name given by Jacobi, and so it's a and the word contact structure kind of like interpolated from this one. So this kind of original contact manifold. So now there is a two version of this projectivize. You can like projectivize, identify proportional vectors with any number constant or only with positive one. So orbit means it's a space of contact element for co-oriented contact element. So I will be just talking about oriented contact manifold, and there is a version of this for non-oriented, but I will not be touching this. So okay, so you take a space of co-oriented contact manifold. This is also can be thought of kind of alternative as a spherical cotangent bundle. Right, so that's you can think of this way. So this is our contact manifold. So now there is this notion of, which I told yesterday, of generating hypersurface. So now suppose you have a hypersurface inside M, and this hypersurface inside M lift to some have always Legendrian. In fact, not only hypersurface, any submanifold in our manifold M lift have a conormal lift. You take all hyperplane which is tangented, and this gives us something. For instance, if you have a curve in 3 space, you have a Legendrian torus in the space of contact element. But kind of for co-oriented surface, it's especially easy because you just take for every point you take a 1 point lift, it's kind of diffeomorphic lift. So you have a sigma and have a lambda sigma which is sitting in this projectivized cotangent bundle. So, and I call it generating hypersurface. And kind of now the statement is the following. You start with some hypersurface, say Legendrian, and now you deform eclipse Legendrian via Legendrian isotopy, and you want to continue cover it by isotopy of generating hypersurface. And again, this is possible up to quadratic stabilization. So the statement is that, again, if you have a deformation on some finite time interval, then there exists some n, some big N, and there exists family. Okay, and so suppose I started with some hypersurface sigma, and suppose I will. This is what I will assume in addition, that this hypersurface is dividing homological to 0. So I will assume that's a regular level of some function. So you start with the hypersurface, which is regular level of some function. So divide our manifolds on 2 parts. And then there exists n, and there exists family of functions ft on M cross Rn. Again, quadratic at infinity, which means that ft of like x of q y is equal some quadratic, non-degenerate quadratic form for y, and plus something with compact support, and such that at the moment 0 you get such that epsilon 0 is equal to 0, and such that it's a generate in the sense what I was explaining yesterday, generate our manifold. So it gives you Legendrian in projectivized cotangent bundle of this big manifold, and then you take reduction and you get back there. Okay, so this is what the theorem. Okay, now I claim that immediately follows from what we proved. Again, modular subtleties with cutting off. Okay, so what you do? So let's compare these 2 contact manifolds, one jet space of M and projectivizes positively projectivized cotangent bundle of M. So this one is has a dimension, say 2n plus 1, and this has dimension 2n minus 1. It's 2 less. So how do I get this from this? So notice that inside this space J1, there exists certain hypersurface, and this hypersurface, like sigma, which is just equal to z equal to 0, right? So the whole 1-jet space is a cotangent bundle times r. And now you're just taking sigma is cotangent bundle times 0, right? So restriction of contact form there is just PDQ. Contact form restricts the PDQ. And now, so this is of course even dimensional, it's not contact, but it's coisotropic with one caveat, that in symplectic case, this kind of, when you do this reduction, then this characteristic fluctuation on coisotropic object always non-singular. And then, but in this case, in fact, this cotangent bundle along 0 section, my contact plane is in fact tangent this one. So this characteristic fluctuation is a one-dimensional fluctuation in singular. In fact, it's radial fluctuation in cotangent bundle, right? It's singularity along 0 section. So I cannot take a reduction of the whole thing. I only can take reduction of this thing minus 0 section. And therefore, when I will doing, I have to be careful not to hit 0 section. Otherwise, I will be in trouble. Okay, so then let's see what's going on. So you take a okay, the second lecture, second hour will be on Blackboard, because this is really, I cannot clean this. So, what we have? We have this m. Remember, we started on m. We had this function, such that I'm drawing the kind of graph of this function, and our sigma was a 0 level set of this function. And I assume that this is a non-critical intersection. There is no critical point of function f on this level set. So now let's take a corresponding, so this was f. So we take this corresponding graphical Legendrian in 1-jet space. So it's a lambda f in 1-jet space, and it's given, again, p is equal df or dq, and z is equal f of q. And now I claim that if you take a reduction of this thing using intersection with sigma, then first of all, intersection with z equal to 0 will not touch 0 section of m, because by assumption there is no critical point on these levels. Is that why I'm not touching 0? And hence reduction is well defined, and what I get precisely this what is generated by this hypersurface in projectivized cotangent bundle. Right? And then I'm kind of doing the same thing. So I have this Legendrian isotopy, and then what I need to care that this Legendrian isotopy extended to the Legendrian isotopy of this graphical Legendrian in the space, and during all this isotopy, I have to care that intersection is transverse, so I don't have any kind of hitting 0, and none of other points somehow accidentally hit this thing, so when I do all this cutting off. But modulo this is, again, immediate correlate. Okay? Okay, so this kind of finishes off this sequence of function, of this proof for generating function, and important that it can be formulated as a kind of Serre covering property for Serre homotopy covering property for appropriately formulated fibration. But then you need to set some kind of infinite dimensional fiber. Okay. So now what are, like, 2 minutes and then I'll stop. Okay. So what is a kind of like immediate corollary of this? So what will be the rest of today? I will be just giving corollaries of all this. So first kind of like thing for which it was proven is of course just Lagrangian intersection theory. So one of Arnold's conjecture was the following. So was this fixed point conjecture which I already was discussing before, but was a kind of like parallel conjecture about intersection of exact Lagrangian submanifold with zero section, right? Suppose you take zero section, you take a Hamiltonian isotopy, and you want to bound number intersection. So as long as it is graphical, then what we get bound in terms of Morse theory on manifold M. Before this kind of all this emergence of generating function and all this stuff, I had kind of some different life where I was doing something else. I thought about the symplectic geometry from long time ago, but I was kind of also doing something else. I was studying topology and tried to prove something in topology. And then I learned something which kind of suddenly, at this moment of creation of generation function, became the same thing, which I kind of have no idea that it's the same thing. So there is a kind of the following theory in topology. So you have a manifold. Suppose you say closed manifold, but it could be also this boundary. We need to kind of to say a little bit the case, but suppose it's a closed manifold, and then for this manifold we can study Morse theory. So then you can Morse theory tell us, kind of relate topology of this manifold with critical point of function on this manifold, and in particular one have a Morse inequality. So what Morse inequality says? Morse inequality says that say number of like critical points of functions are greater or equal than the rank of homology of the manifold. So you can, there's the nuances, you can talk about what coefficient you take, kind of, but that's what it is. So now, but but this is not only bound for the number of critical points. So if you have a, say, manifold is simply connected and has a high dimension, then Smale theory says that this is essentially exact bound. So you can always find function with this minimal number of critical points. But if manifold is not simply connected, then of course this is extremely bad bound, because for instance you take a M as a homology sphere, could be, and then it only says that only 2 critical points, but of course it's not true, you have to have much more. And so there is a much more kind of like, there is a this question of the bound. In this case it's very kind of well again studied in topology theory. There is some called Charcot inequality. There are some kind of many results of what it is. So, but this is only true in the non-degenerate case. That means that f is a Morse function, all critical points are non-degenerate. Then you have this thing. For instance, for if m is a torus, m is a Tn, then you get here 2 to the n, and the 2 to the n, but on the other hand, if you have, say, 2 torus, we get 4, but in principle, you can, if you try, you do not care about non-degenerate, you can put these 2 critical points on the same level and find function with 3 critical points. So there is a kind of another bound, like so a minimal bound for like not assuming non-degeneracy, and this bound is a well-known bound in terms of cup length. Cup length of the manifold plus 1. So what is cup length? You take a cup length of the manifold is a maximal number of classes such that the product of this cohomology classes is non-zero. So cup length of 2-dimensional torus 2, and therefore it's 3. So this is called like Lusternik-Schnirelmann bound in terms of cup length. But again, this cup length bounded term is not best bound, and I'm not sure. So there is a kind of actual bound is in terms of what is called Lusternik-Schnirelmann category, but they are not the same. So again, I don't know all results where it's exact, non-exact, but definitely not always. So we have this thing. So anyway, so let's denote by Morse of M. We'll define this infimum of number of critical points of function in this non-degenerate case, and Lusternik-Schnirelmann number of manifold. This is the infimum of number of this critical point, number of critical point of function in kind of without assumption of non-degeneracy. So you have this thing. So now you have, there is something in topology called stable Morse series. So in stable Morse series says the following thing. So take our manifold, and well, exactly like in what I was doing, though it's kind of like not clear why it's the same, but it was exactly the same. So take manifold, multiply by Rn, and now here on this manifold, again, you consider function precisely of the form which I said. So you take a non-degenerate quadratic form. So for instance, you have xy, or I write again qy. So you write function q of y and plus this compactly supported function epsilon qy. And notice that this compactly supported, it's kind of, again, as I already explained yesterday, is not so important. Important this function grows at infinity of y is slower than quadratic. Then you can cut it off and without creating any critical point. For instance, you can add linear function in y, it's still good. So you try to minimize number of critical point on this function, and then you get, like, you can say corresponding number, you can say stable Morse number and stable Lusternik-Schnirelmann number. So of course stable number less or equal than actual Morse number is the same here, right? Because you can always add quadratic form, you get the same number, but maybe you can do better. So it was well known. So these two inequality also holds for stable number. So this is a bound for stable number, and this is a kind of obvious, because you see how you can think. So of course, kind of like you can think in terms of like homology, writing some exact sequence, etc. But it's kind of obvious, right? How this like Morse number, how this Morse and also Seifert and Transfer and kind of these people, how they thought about this Morse inequality. They say, okay, so you take some cycle and you're trying to kind of like push the cycle, realize the cycle in such a way that it kind of like maximum of function on this cycle is minimum possible. So you take like on the torus, you have this piece of cord and you're pulling it down, and then it would hang on some critical point. So you get kind of like this is a like geometric reason for all this Morse inequality. And now if you have a function on our manifold, this is a graph of function on our manifold, and you say, for instance, you add function f minus y squared, then you get function like this. And then for every cycle on our manifold, you can multiply the cycle by this unstable manifold of this quadratic form, and again you're trying to pull down this one, and then it would again hang on some critical point. So you can anyway. So there is this kind of stable Lusternik-Schnellmann and Morse inequality. So what corollary of what we proved, that minimal number of intersection of Lagrangian Hamiltonian isotopic to zero section with zero section is actually equal to this stable Lusternik-Schnellmann or Morse number, depending whether we want intersection point transverse or not. Right? So that's what corollary of this. So it's a kind of fantastic coincidence. I don't know how it's happened, but this quadratic stabilization, which kind of existed for ages in topology, kind of studied, and in Morse theory, somehow turns out to be exactly quadratic stabilization which appear in the theory of generating function, and kind of visibly by completely different reason.
Stable number is attained for some n, which is dependent on the dimension of m.
So there is a because only finitely many possibilities. So of course it's attained by some n.
But what I want to know is, depending on the dimension of the manifold, can you control
Can you control n?
capital? Yes.
Can you control capital N? Yeah, I'm pretty sure that yes. I'm sure it should not be more than, say, dimension of the manifold for sure. Okay, maybe. Yeah, because of some kind of transversality reason, kind of like if you multiply by something bigger, then kind of like yeah, I think so, but kind of I never thought about this. So and in many cases, the stable number is in fact the same as the unstable number, because in the case when unstable is precise in Morse inequality, then you have the same thing there. But there is a kind of, I already forgot all this thing. But for instance, in non-simply connected case, there is some extremely subtle question about group ring of fundamental group, which kind of related to this problem about this relation between stable and unstable. Yes?
Yeah. So in the generating function case, there was this increase of dimension going up to infinity. That is somehow not seen.
Yeah, that's here. That's I think not happening. Okay, so that's what we have. So now there exists kind of one one more subject where again pure topology subject where quadratic stabilization kind of was used, and again long time before any kind of symplectic stuff appeared. Namely, so by the way, I am not giving proper references. Okay, who is the kind of author of this idea of this generating function depending on this extra parameter? So, okay, so like probably if you take so if you ask Arnold, he would say Jacobi. And indeed, he kind of like showed me once the paper of Jacobi where kind of something you can interpret as this definition of like a draining function, but it kind of like precise sense is due to Hermander. So okay, so now I can back to geometry. So there is a let me talk about this object called pseudo-isotopies. So this is the following notion with due to Jean Cerf, and so it's the following thing. So what is a pseudo-isotopy of the manifold? You take a manifold and okay, it's important that it may have a boundary, but to start I suppose it's closed. And you take a M cross interval. So you take this cylinder. You take a cylinder, and now you consider diffeomorphism of. So there will be two definitions of pseudotopy. One, so you consider diffeomorphism of the interval. You have a diffeomorphism of the interval which preserves top and bottom. Moreover, I want that f on M cross 0 is equal to identity, but I only want that f of M cross 1 contained in M is equal to f M cross 1. So it does something kind of unknown to me on the top and identity on the bottom. So of course there exists isotopy. So suppose you have an isotopy. So suppose you have say some family. Maybe let me call it F capital, the pseudo-isotopy. And suppose you have an isotopy. So that means you have a M to M. You have a family parameterized by interval 0, 1. Then of course you get pseudo-isotopy, but which in addition have a preserve every level, right? So this is kind of will be trivial pseudo-isotopy. But kind of like general pseudotopy does something terrible with this level set. So this kind of question which Cerf studied, what is the space of pseudo-isotopy, what is the topology of this, is it true that any diffeomorphism, say pseudo-isotopic to identity, to the one which is kind of like isotopy, etc. Yes?
Sir, F is an isotopy, right?
F capital is called pseudo-isotopy.
Yeah.
But I out of Ft I can make kind of trivial pseudo-isotopy, just defining on each level to equal to Ft of level T, right? Okay. So this F of Xt is equal Ft is equal Ft of X. So the space of isotopies inside pseudo-isotopies, of course, contractible space, because it's just space of paths with one fixed point, but the other point is not fixed, right? Okay, so now this what Cerf kind of like observe, that in fact, in order to understand this, we need to understand parametric Morse theory. Namely, let's consider the following question. So this let's call the space P of M, space of pseudo-isotopy. And I will define another manifold, which actually Cerf denoted E of M. And this is a space of function on this M cross I to I will write I instead of 0, 1, m cross I to I, such that f of x0 is equal 0, f of x1 is equal 1. So you take a space of function on the product, and such that f has no critical point. You take a space of function on the cylinder, which are constant, and we can say near the boundary if you wish, and no critical point. So claim this E of m is homotopy equivalent to P of m. It's the same kind of reincarnation of the same space. Why? Because, of course, so on one hand, there exists a map. There is a map. You can take a, if you take any f, any this f capital in P of m, you can associate with this f, just take a, say, let's call this, there is a kind of trivial function, just projection. Let's call it pi. So you just take a pi composed with f. Right? So you have this map. And now I want to define homotopically inverse map. So what is homotopically inverse map? You take this function. Suppose you have this function. And now choose any metric and choose a gradient vector field. And you can, of course, every gradient line grow from bottom to top. And therefore, you can parameterize this gradient line precisely by value of the function. Right? And of course, this gives us system of coordinates. This gives us diffeomorphism to m cross I, self-diffeomorphism. And so, and it's kind of like, if you think for a second, this is a homotopically inverse map to each other. So okay, so this is a self pseudo-isotopy space. Now there exists definition of stabilization. We also, you can find what is called stable pseudo-isotopy space. And at first hand, it's completely unclear why this has anything to do with quadratic function. So we have a, so suppose you have any pseudo-isotopy f. And let's first think about this as a diffeomorphism. So then with this pseudo-isotopy, we can associate with this pseudo-isotopy you can like now I take okay first of all let's kind of slightly generalize notion of pseudo-isotopy to the following situation. So I allow manifold to have a boundary, but then over the boundary I want pseudo-isotopy to be trivial, to preserving level set. So okay, so suppose you have a m cross I, and then I want to stabilize it. So that means I want to define isotopy on m cross I. And what I would like to say, that f of x, so what is this kind of f hat? F hat, kind of what I would like to say, f hat of x t u is just equal to f of x t u. So first I can write something stupid, but then this is a kind of on the spot is not pseudo-isotopy, because look what happened. So I take so suppose this was my original cylinder, and now I multiply this original cylinder by interval, so I got this cube. And now where my maps as identity. So of course, because I just this is our map is just identity along this one. So it's identity on the bottom, but well, it's identity here, it's identity there, but it's not identity over this one. So you see, there is a kind of like picture like tennis ball, right? So you have this. So you have a boundary of this cube is split in the two disks. One is a union of these three faces, another union of these three faces. And our stabilization is a diffeomorphism which is identity on this thing is not this. And so it's not quite fit in the definition. I would want to be identity over the whole this thing except the top. So you need to reparameterize boundary to do that. So that's how it's done. But there is a much cleaner reformulation of this in terms of function space. So in function space, I say, so I'll define pseudo-isotopy now the following way. Stable pseudo-isotopy, I will define exactly as we did with our quadratic stabilization. So suppose I started with pseudo-isotopy, and the pseudo-isotopy I think is a function. So remember it was m cross I to I was function. But I kind of don't like this function. I would like to replace it by m cross r to r, but then I require that this function is kind of standard linear function at plus some outside some domain. So you have a function which kind of like something, and then it kind of linear function there. So this is, and this function has no critical point, right? So now I say, so this is unstable isotopy. But now instead of this, I write this is a function on m cross r n times this again Rn. And now this function, which I want to do, I want this function to have the following form. It's equal. So let's call this coordinate t and this coordinate y. So and this coordinate say x. So I want my function have the following form, this like stabilized function, to be f of x t y is equal t plus quadratic form of y and plus something again with compact support. Right? So I add quadratic form. So
Where's the phi? Phi is in epsilon.
why the r?
The phi, the original phi.
Why? Where is it?
This phi.
It's notation. So I didn't. No. Oh, okay. No. Here. Yeah. This my phi. This my phi I could write as a t plus epsilon. Right. It's some kind of perturbation of function t. And then you can have this one. Okay? So why this have anything to do with my previous thing? So how this can be interpreted? Because like look at this function. So here, for instance, again I'm drawing this q like minus y squared. So just look like this graph of function. So now you take a level set of this function far below. Far below, this is just quadratic function. So this is kind of standard disk here. And then I take a level set far above again. And this is my kind of like pseudo-isotopy in kind of original definition. We take a level far away, level far below, and in this x, in the t direction, the vertical level far away. And this cut off this my function. Okay? So this is a kind of like pseudo-isotopy. So there is a map, and turns out that there is a theory. So that you can pass to the limit. It's called stable pseudo-isotopy space, and the stable turns out that homotopy groups stabilized. They stabilize, I think, something like best world record around 1/3, so I mean, no, I mean this kind of what is the dimension? So you want what is the dimension of manifold such that homotopy group after stabilization remain unchanged, and I think the result of Igusa theorem is that it's something like n/3, and probably there is some example when you cannot do both. So I am not sure what is precisely the status, but something like right. But anyway, but the importance they stabilize. So now immediate corollary of what I proved. So I already said one corollary is that you have a bound on Lagrangian intersection of deformed Lagrangian with zero section in terms of stable Lusternik-Schliemann Morse numbers, right? By the way, you know, there is a kind of something called Arnold conjecture. So essentially, like you know, like in like tradition in symplectic geometry, that almost every conjecture is Arnold conjecture, and every integer is Maslov index. So, but kind of like approximate, good approximation. So, but there is a kind of not precisely known kind of what is exactly Arnold conjecture. Well, about certain things, of course, it's Arnold conjecture. About other which called Arnold conjecture, but I'm not sure Arnold ever said this, but kind of doesn't matter. So, but in particular, what Arnold says. So, kind of Arnold, of course, said that everything should be bound in terms of Morse theory. That's Lagrange intersection bound in terms of Morse theory. But what precisely this mean? And what does it mean to prove Arnold conjecture? So for instance, we proved that minimal number of intersection is at least, say in transverse case, at least stable Morse number. But there are examples when stable Morse numbers really less than unstable Morse number. It's not necessarily the case. But I don't know examples, any example, when you can get a Lagrange intersection with less than actual Morse number. So again, you have a manifold. It has to be non-simply connected, such that minimal number of stabilized Morse function is less than minimal number of like function on original manifold. So quadratic stabilization really decrease minimal number of critical points. So any best known proof of Arnold conjecture give bound in terms of the stable number. Nothing better than this is known. But one would say, let's take this manifold for which stable number is less, and is it really true that there is any example of Lagrangian such that minimal number is actually less than Morse number? It's greater than stable number, but less than Morse. So it would be interesting to understand, but this is open question.
What was the connection to the group ring that you were talking about in the case of non-simply connected fundamental group?
Not simply connected fundamental group. So what was this? What was the stable Morse number? I think Yeah, so you have to, I already forgot, but I think you take a group ring as a module over group itself, and the kind of like you ask number of generation of these models, and kind of you want to have a rank bound for this rank. Okay, so yeah, so I'm saying this proof Arnold conjecture, but what is Arnold conjecture in this case? Because kind of Arnold never kind of formulate anything about stable numbers, so kind of probably you can say maybe he meant that should be bound in terms of just Morse series. So therefore, if you construct this example, you disprove Morse Arnold conjecture and will be famous. Yes. Okay, so. And I'm not sure that it's completely impossible. I don't think people really kind of like tried hard this. So, but let's return now to, so this was I already formulated, but now let's return to the pseudo-isotopies. So let's do the following construction. So take any manifold, and let's take a again, consider manifold cross R. So take this cylinder, and in this, and now you take a cotangent bundle on manifold cross R. So in there is a like what are coordinate, let's say like coordinate QT, and there is a dual coordinate like P and say U to this one. So in cotangent bundle, you can take a Lagrangian, which is a graph of function dt. So that means that you have a like u is equal to given u equal 1. Yes, right. So you have a like so graph of function dt. So u is equal 1 and p is equal 0. Right. So you take this like so it's a kind of parallel to zero section Lagrangian. There is a zero section, and they are kind of shifted by 1 in u direction. So now you consider this. So let's call it L0, zero section, and this is L1, not L0, maybe. Okay, I will write maybe. I call it 0 before. Kind of take it 0, possible LT. Which has, so let's take the space, well, maybe I'll write this L0. So let's just take a space of all L, which sits in cotangent bundle of this M cross R minus 0 section. So this L0 sits in the, it does not intersect 0 section. So I consider space of all L in T star of M cross R minus 0 such that L, which so take such space of this one, which at infinity such that L coincides with L0 outside a compact set. So take a space in, so I said take manifold M cross R. In this manifold take in cotangent bundle take 0 section, and take also this 0 section shifted 1 in the direction of this like graph of function t dt, graph of function dt. So take parallel 0. And now I consider space of all possible Lagrangian which are coincide with this L0 at infinity. And take a component of an L0 in the space. So it's space of all possible Lagrangian coincided with this L0 and take a component of this one. So let's call it lag.
There is a confusion question. So you're deleting the zero set and you're asking the Lagrangian to coincide with The zero set?
No,
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 the zero is a shifted copy. Okay.
Z0.
It's a shifted copy.
Yeah, right.
Okay. Okay.
So I remove zero section, and I consider this all this Lagrangian.
L0 is a shifted copy.
Yeah,
That zero has nothing to do with zero section.
yeah, okay.
It's a shifted
Maybe I should call it L1.
Yeah, I also had the same.
and you're looking at pi zero of this whole space and taking one of those elements, is that?
Not pi zero, just take a component of this. Yeah. Take this component and call this component lag. Component.
Can you explain that concept again?
Take a potential one of m cross r. Then there is a function t which is a projection to r. So if you take a graph of dt, it will be Lagrangian parallel to zero section.
Yes.
Right? It's kind of like in this coordinate, like as I say, pq, where did I write? Okay, I erased it already, but you have a coordinate, say q, t, and the dual coordinate, say pu, and you have a something given p equals 0, u equal 1. So it's kind of parallel Lagrangian.
Equal to 0, equal to 1.
Yes? It's parallel Lagrangian, does not in the complement of zero section. And you consider all Lagrangian which kind of at infinity outside of complex set the same as this L1. But only you take, I don't know, maybe it's connected and disconnected, I have no idea. Probably it's okay. Yeah, but yeah, you take. Okay. No, what I'm saying is wrong. It's not what I want. Okay, not taking commutative identities, just take the whole space of all such Lagrangian, and take the space of all such things. And then I want to ask.
You are still assuming that they agree with that now.
I agree with that one, but I forget what I said about the component commutative. Okay, so now I want to understand what is the topology of this. So in particular, I want to understand what pi 0 of this lag and kind of pi 1. I want to understand what is the topology of this thing. So for instance, are there two which are not isotopic of this type? So now let's notice that pseudo-isotopy space this pseudo-isotopy space, and I write it in this incarnation of this E. Pseudo-isotopy space of M is a naturally sit there as a subspace in this lag. Because if you take any function on M cross R without critical point, its graph will be in this space. Because at infinity this function is standard. Right? And therefore, you can kind of to see what is what this homomorphism of on E of M to homotopy group of lag, what it is gives, right? And what?
So we are taking a function from M cross I to I.
Okay, I already ran away from I long time ago. I said let's think about that isotopy not as function E space, not as function M cross I to I, but as function M cross R to R, which at infinity is just linear function, just T. So you have this this inclusion, and the theorem that this map is a kind of injective. This homomorphism. Okay, let's call it J. So J star is injective on stable homotopy group. On stable homotopy group. So as I told you, this homotopy group of this E stabilizes. For instance, if K is less than 1/3 of dimension n, then as dimension grow and as I stabilize, nothing change. So this map is injective on stable homotopy group. So now, so it gives you kind of, okay, so one would like to understand what are stable homotopy group of this of pseudo-isotopy space is, and this is a kind of like this is a source of the whole pseudo-isotopy theory is a reason for existence of algebraic K-theory. So algebraic K-theory was created kind of originally precisely to answer to compute kind of homotopy group of this thing. So for instance, what is a like pi 0? So pi 0, that there is an answer in terms of like so-called second Whitehead group. So there is a theorem by Hecher-Wagoner which computes this, and then it was a kind of huge development of this thing which was computing this homotopy group, and there is a theorem of Waldhausen which give answer in terms of some algebraic K-theory.
Is there a reason why this should not be, at least asymptotically, an isomorphism? I mean, on the right side for the pi k of Lagrangian, there are new elements that one gets. Is that possible? I mean, this is injectivity. Is there at least some form of surjectivity?
You see, there is I think that surjectivity in all this thing is kind of tightly related to all this problem about nearby Lagrangian conjecture. Kind of like if you know that all this everything getting by this one, then there is some kind of way of understanding what the image is. But could be some wild thing which have no idea what is there.
Sorry, is it connected to the usual stabilization in homotopy theory by taking suspensions? Are the two things related?
Okay, so in homotopy theory, like I don't know, of spheres of everything, so you take a suspension, but in the like stabilization for the pseudo-isotopy space is done via this quadratic stabilization. So it's probably don't want to say that it's unrelated because it's maybe related, kind of like, but kind of not so obviously how. It's I think probably standard like stabilization was special case of this, but kind of.
By stable homotopy, you mean that suspension management?
No, it's
Stable. So the statement is the following. So when you take a pseudo-isotopy space, then there is this operation of stabilization, as I said.
Yes.
And the theorem of Hecher and then also Igusa, which said that this map stabilization is stabilized on homotopy.
Yes.
So that means that if you like go, if dimension of the manifold is like 3 times more than the index of homotopy, then when you stabilize it, it's isomorphism.
So by stabilize, you mean?
By quadratic stabilization, which I said. Okay. And so stable homotopy, so unstable pseudo-isotopy group, I think it's kind of like some mystery. I don't think much known, but stable homotopy group of the things they computed in terms of this kind of like algebraic K-theory. So in particular, even if you take our manifold is just point or Rn, which is the same thing up to stabilization, if the manifold is just a point, then this is so what we get is algebraic K-theory of integers. And algebraic K-theory of integers is extremely kind of like subtle thing. So I think it's completely computed over rational I think the answer is in dimension 4k plus 3, there is some rank q. So it's a kind of, there is an answer, simple answer in rational, but then I think the world record in kind of distortion up to dimension 11 or 12 or something like that. So, so not hard. So it's hard to compute. But it kind of, they highly non-trivial, kind of like, I could write down the table of this up to dimension 11, but probably it's not so interesting. So anyway, so how this is proven? So why this is proven? So okay, maybe you need to write some of this appropriate exact sequences for the self vibration, which I told you, but like intuitively it's very clear. So for instance, suppose I want to argue on level of pi 0. So suppose you have a non-trivial element or stably non-trivial element on pi 0 of pseudo-isotopy, which require manifold to be non-simply connected. If manifold is simply connected, then Cerf theorem, the stable group is 0. But if it's non-simply connected, then you have this computation done by Hetcher and Wagoner, and kind of there are plenty. For almost anything, all finite group, they're kind of non-trivial. So you compute what it is, so you get some element, and then this gives. So I want to prove that if a stably non-trivial, then this Lagrangian which we get is not isotopic to flat one. So there is an indifferent homotopy. Suppose you have this homotopy. Then this gives us deformation. You can cover this deformation by generating function, right? So you can take standard and generate this by this thing. But stabilization exactly the same in the theory of generating function as in the theory of pseudo-isotopy. So therefore, what I get this kind of like element of the stable pseudo-isotopy, and because it's non-trivial, then it is therefore this Legendrian is not trivial, because otherwise you'll get this trivial element. Okay, so there is kind of like, if you try to kind of properly argue, there is a little bit more there involved, because in fact what you need to prove that the following thing. So you need to understand what is a topology of the space of generating function which generate, like for instance this L1, or generate some fixed Lagrangian, like 0 section. So this is a family of generating function which are fiber-wise quadratic at infinity, and have a fiber-wise have exactly one critical point, right? So this space is not trivial. So the space of function on Rn, which is quadratic at infinity with one critical point, is not a contractible space. It's kind of, it's a little bit related to pseudo-isotopy space, so there is some non-trivial topology. But what is important, that the space of like this so the space is a contractible in the space of all pseudo-isotopies, kind of on this one, of stable pseudo-isotopy. So the fiber, so you get some self vibration where fiber is not contractible, so you don't get really kind of, but it's contractible in ambient space, and this is good enough. So there is something to argue, but it's a pure kind of elementary topology. Okay, so this is it. So now there is a kind of two other statements which I want to say, and obviously I cannot prove it today, but at least I will formulate it. So there exists, this theorem is actually, this is written in our paper with Gromov, the same paper. But there is some other observation which kind of we proved with Thomas Krah. And which kind of give some Legendrian version of this. And the statement came out of our unsuccessful attempt to use it to construct counterexample to nearby Lagrangian conjecture. So this statement kind of looks. So I'm kind of, by the way, I'm still not completely sure that somehow this cannot be used, but not the way as we tried. So you see, so you have this non-trivial example. So what it says? So it has in the what nearby Lagrangian conjecture says. Nearby Lagrangian conjecture in this context would say that let's forget this about zero section and take just this one Lagrangian and consider, say, space of all Lagrangian which coincide, but without this extra condition that they don't intersect zero section. And you want to say, are there non-different element, is it connected or not, the space, right? That if it's disconnected, if you construct it, and what this construction give, it can give you only this element, but in the complement of this one. So kind of there's obvious idea, right? So let's kind of try to do this. Take this zero section, kind of maybe let's bend this section like this, and take some kind of like piece and implant there this non-trivial pseudo-isotopy, right? So you get this something. So this looks like great candidate for something which should be not Lagrangian isotopy. But turns out that it is. And it is like Lagrangian isotopy. But as I kind of explained, well, probably maybe I should postpone it for tomorrow. So the fact that it's kind of trivial yield some non-trivial element in the space of Legendrian.